Good day, everybody. We continue with our discussion on non-uniform quantization. As you may remember, we are in the lookout of a very convenient transfer characteristics for the quantizer, which will result in a signal to quantization noise ratio SQNR almost independent of the amplitude distribution of the input signal. So, in the process, we define the output characteristics as y equal to some function of x c of x, and we listed two desired property for this Cx. One is that it is an odd symmetric function, okay, monotonically increasing function, and then the Cx function has to be bounded after all by these extreme values of plus v minus v and 0 in between. And towards that we started developing some basis for finding a convenient form of Cx, and there we used an approximation for the slope of that curve d dx of Cx. We wrote that approximately let it be 2 v by m, which happens to be the step size for a linear quantizer, okay, into 1 upon delta k, where delta k is the kth step size for this non-uniform quantizer. And I guess we were here somewhere, okay, where we defined ultimately the probability that x, the input signal, lies in the interval I k, that is between x k and x k plus 1, okay, and that probability I wrote, I am introducing a new symbol here as p of k, which by definition is the probability that x lies between x k and x k plus 1, and this should be equal to p of y k times delta k, where p of y k is the approximation of p of x PDF, and we assume that p of y k is constant in the kth interval, okay. And it is obvious that summation of this probability, total probability, will be 1. Now let us try to find an expression for the quantization noise power, which is nothing but the mean square error for the error value, and then again if E denotes the quantization error as we were doing for the linear quantizer, we can write E as the difference is specifically yk minus x. You could also write it as x minus yk, but I am following this notation, is yk minus x when x is in the kth interval between xk and xk plus 1. Let it be equation number 9. So now I can write an expression for the mean square quantization error, okay, is x minus yk. I have changed it deliberately, I mean it is immaterial ultimately, square times px dx. This is a general expression when x ultimately varies between minus v and plus v, okay, and then making use of equation 8 which I noted just now, okay, we can observe that p of yk, which is a constant probability density function PDF within the kth interval, is pk by delta k, where pk is the probability that x lies in the kth interval. Is that okay? Just briefly going back, in this expression we can see that pk is p of yk delta k. So I am writing p of yk as pk by delta k, simple substitution, okay. So now equation 10 now can be rewritten in this form, that E square bar is pk by delta k, integration is only over kth interval, okay, and sum of all these quantities when k ranges from 0 to m minus 1, x minus yk whole square dx, integration of that. This is equation number 11. So truly speaking, this expression itself is a bit approximate, okay, it is a bit approximate because we have assumed that the probability is constant within any particular interval, okay. So to that extent this expression is approximate, okay. Now we have already noted that yk is the mid value of the kth interval, and hence yk is half of xk plus 1, okay. It was equation number 5 earlier if you refer back, and then after integration of equation number 11 which I showed just now, one can ultimately find that E square bar is 1 upon 12 times summation of p k delta k square, k running from 0 to m minus 1. This is a somewhat convenient expression really. Okay. Summation of p k delta k square, k varying from 0 to m minus 1. Let it be equation number 12. Now, we had another approximate expression for the slope of y equal to cx curve, if you remember. So, recalling that expression, we can write now, we can make use of that expression, which was equation number 4. I can write an expression for delta k approximately is 2 v by m times 1 upon d dx of cx. I am writing is that d dx of cx inverse of that. Okay. So, what I am going to do, obviously I am going to replace this expression for delta k in equation number 12. Okay. And that results in a different looking expression for E square bar, the mean square error, which is v square by 3m square times summation of pk times this d dx of cx 1 upon d dx of cx whole square. Okay. M, what is m? If you remember, is a number of intervals, okay, the number of levels, and v is the maximum amplitude that the input signal can take. Okay. So, this is a modified expression for the mean square error. That expression, equation number 14, can now be equivalently expressed in this form. You have to tell me how. You have to tell me how I can write equation 14 in this form.
PK is basically the probability.
Pk is the probability.
Xk to xk plus 1.
Yes, in the kth interval.
0 to n minus 1 it will become plus 2.
Yes. Okay. So, using a set of previous equations from 5 to 8 to be precise really, one can easily get this expression of E square bar is an approximate one, is v square by 3 m square integration of integration over minus b to plus b of this quantity px times d dx of cx inverse to the power minus 2, let me say it is 1 upon d dx of cx whole square dx. Yes, please.
Here we are integrating that and we are taking cx varying continuously.
I have brought it back now.
This should be more exact than just being approximate.
Pardon? Why is this approximation is your question?
Yes, it should be more exact than the previous equation.
Not really. In fact, we have arrived at this expression by using equations 5 to 8 and retaining the approximation of equation 4. In equation 4, if you go back really, okay, see I am considering this whole thing as a parameter. Okay. So, I do not want to break it further really, fine. So, to that extent there is an approximation already involved in this expression, which is reflected here in v m along with this d dx of cx, they are here because of that approximation in equation number 4 earlier. Okay. So, this equation is still approximate. Okay. So, this is an expression for the mean square error, and hence it is the expression for the noise power. Okay. Sometimes we also write it as the variance of the noise process. This the noise, ultimately quantization noise being a random phenomenon. Okay, we can also express it as the variance of the corresponding noise process. Okay. So, you will find alternative notations of sigma E square to indicate this mean square error or the noise power equivalently, or another notation in some book is sigma E square. So, I have found an expression for the noise power. Can I find an expression for the signal to quantization noise ratio? What do I have to do? I have to find the signal power expression. Is that going to be different? No. We are talking about changing the characteristics of the quantizer. We are not talking about changing any characteristic of the input signal really. So, the input signal power expression will be the same as we had obtained earlier for the linear quantizer, okay, and this is the general expression, equation number 16, okay, and hence I can now find an expression, I said not a very shortened or simplified value, a somewhat big looking expression, okay, for the signal to quantization noise ratio for non uniform quantization. Okay. So, SQNR by definition should be the ratio of the signal power expression and the noise power expression, and it looks like this simple substitution of signal power from equation 16 and the expression for the noise power from equation number 15. Okay. Now, this is a very interesting expression really, equation number 17. Just look at the form of the numerator and the denominator, okay. Leave this portion aside. These are something to be decided by the by other issues really, the number of levels that you wish to have and the maximum voltage range for the input signal. Okay. Now, if I now ask the basic question, starting question of choosing Cx such that the signal to quantization noise ratio is almost independent of the signal amplitude distribution or the statistical feature of the signal. Can I get a clue from this expression number 17? Yes.
Cx is equal to 1 minus.
So, we can find that if I can make this ratio independent of the signal and its probability really, then I achieve an expression which is independent of the signal probability and other issues, is not it? And it is very obvious the way I have put, I have only just put Px first here, I could have written this expression in the numerator as Px times x square that way. So, I can now find a relationship so that we can cancel this ratio out really. Okay. So, we say that for a robust performance the SQNR should be almost independent of Px, the signal amplitude distribution or the statistical feature, and then we can get a clue from this equation number 17. And yes, as you suggested, this desired condition is this. The desired condition is that d dx of Cx, that is the slope of y equal to Cx curve, should be some constant times 1 upon x. Sorry. So, then the thumb rule is that if you are going to design a non-uniform quantizer, okay, the transfer function should be such that, okay, the slope of the curve is proportional to 1 upon x. Okay. What does it mean? To make it simpler, if the amplitude of the signal is larger, the slope should be smaller. Is that okay? Is it somewhat matching with our starting diagram which I showed uh, previously? Look at this diagram really. Okay, at least in some portion here, this feature is common quite, that when x amplitude of the input signal x is smaller, the slope was more. When the amplitude of the signal was higher, the slope was less. Okay. So, ultimately it has to be a curve such that it rises fast initially for smaller amplitude of x, and then it rises rather slowly for larger values of the input signal. Okay. And this whole thing theoretically I now add should be valid for the whole range of the input signal from minus V to plus V. Okay. Now, this is a more mathematical expression, it was fine. Now, let us see, I mean we have certain boundary conditions to achieve, is not it? We want a transfer characteristics y equal to Cx such that it is also bounded to plus minus V at the extreme ends, and it also passes through 0. Okay. So, when you put that boundary condition, okay, the extreme conditions that the signal Cx passes through plus minus V only, I get this definite expression. Okay, we get an expression of Cx is equal to V plus k ln x by V. Ln is the natural logarithm. Okay, x by V, where V is the maximum amplitude of the input signal x. Okay, for x equal to x greater than 0. Okay, tell me, yes, the same thing, because I know Cx is a function which has got odd symmetry, isn't it? Okay, so I know minus of Cx is C of minus x. So if I give this expression for positive values of x, I have the corresponding expression for the negative values of x as well. So this describes the thing. Okay, but are you totally satisfied with this expression? No. Yes. Why? Yeah. So we have been able to satisfy the two extreme points. Okay, so far as the boundary condition is concerned, but still at x equal to 0, what happens to this expression? Hmm? Ideally, it should be 0, isn't it? When the input signal is 0, I mean the quantizer output also should show 0, isn't it? Then how to solve this problem? This again is a moment where, I mean, fundamental science perhaps does not give you the answer directly, and you have to approach, I mean, come out with some engineering approach and engineering solution to the problem. So we are quite close to achieving our desired aim, isn't it? I can say that at this point this expression looks good, okay, for designing my non-uniform quantizer, okay, only when the input signal is non-zero. Okay, but if the input signal is close to 0 or even exactly equal to 0, the quantizer output is not defined by this expression really, isn't it? So we want to now modify this mathematical so nice looking expression so that our practical purpose of designing a quantizer is ultimately served. Okay, just to give you a brief uh, overview, this is the usual nature of the curve for y equal to ln x, is it not? Some a times some constant times this, is it not? Okay, so now, and when, if, just consider the Cx is something similar to this, fine, and so I had the other part also defined. Maybe if I draw freely, it would be something like this. So so far the theory that we tried to develop, an approximate one, of course, in fact that approximate theory told us that, well, you should be using this kind of characteristics, this kind of characteristics here, and this characteristics for this half. Okay, so for negative values of x, this curve is to be used. For positive values of x, this curve is to be used. Now try to be an engineer momentarily and tell me whether I can find out a balance between the mathematical solution and my engineering realizable characteristic, transfer characteristics. Yes, one suggestion is one at a time. His suggestion is shift, it means this curve. So one suggestion is shift this curve to this side, okay, to right, so that this point collapses on this or 0, 0. Okay, so something like this. Okay, this one is to be shifted to this side. Is that the suggestion? That's the first suggestion. Somebody has another suggestion, I guess. So this curve, let me use some other color. Say this curve then shifts to a position like this. Okay, then what do I do? So he has perhaps solved the problem of making the curve transfer characteristics pass through 0. Okay, but what happens to other values? So some positive values of x, do I have to add these two or subtract or do something? I have to do something, because otherwise for these small values of x I have got two possible values allowed, this one and this one, from these two characteristics. So what do I do? Pardon?
Clip the values are above the x-axis. Like for in the case of the left-hand curve,
Left hand curve is this one, original
clip
one.
the values above the x-axis and then like shift it. So like you, what you get is then one continuous curve.
Ultimately, we would like to get a continuous curve. That's a very important point, really. See, pardon? By the simple shifting, so it should not be so simple shifting. Yes, that's a point. Okay, so simple shifting, even if we do for just matching over here, okay, we have to again satisfy this end points. The curve has to go through this. Okay, and as he says that ultimate whatever engineering approach we apply, really ultimately we would like to have a smooth curve, really. Okay, we would not like to have a curve such that, I mean, we have this kind of zigzag multiple values etc around the small value. Pardon? After this shifting, yes, right, right. Okay, let me hear. There was some session in this side. Is there any session here? Okay, it's taken care of. Yes. Y equal to x beyond a within a certain range. Okay. Yes. So one point is that the solution need not be unique. Is it not? Because it's an engineering solution, it need not be unique as such, really. As somebody has very rightly suggested that, okay, we need not shift perhaps, okay, because then shifting again will shift these endpoints as well. Let them be as they are, really. We go for some kind of linearization in between. How is that? That okay? Yeah, like this kind of approach. I draw a y equal to x curve, okay, and linearize it, and we say that this logarithmic nature is followed beyond a certain range of the input signal. How is that? It solves the problem, really. At least these boundary conditions are satisfied. Okay, this composite curve now passes through the origin. Okay, though I cannot describe it anymore by that simple expression. Okay, but it serves the purpose perhaps. Somebody may say that, okay, why do we use one segment? Okay, because in this case, I mean, the range over which the we are using y equal to x, the range for x is somewhat higher. I would like to break it in two parts. Then, okay, let this linear approximation be over up to certain range, and after that I change the slope to some extent. Okay, two segment description, go closer to this and have an intersection at a closer point. Okay, so many possibilities one can think of, really. So what we will now talk about is the two standards which have been suggested for this. That's a simpler one to understand. Okay, a single segment, single line segment. Okay, and then it is also simple in terms of implementation. If we have to implement the whole thing, say using some analog circuitry, the one I suggested is that instead of using one line segment, you may like to use say 3 line segments, one around 0, okay, one for this positive part, the other one for the negative part with the same slope, but the slope will be somewhat less than this 45 degree, isn't it? So that will be somewhat closer to the y equal to log x function, even for somewhat smaller values of x. If I say that up to this it was x, we are using the curve straight line, okay, with a slope of 1. Then if I use a more than one line segment, I could make it linear from this up to this point, and between this point and x line I could use another straight line with a different slope, so that it catches up with this logarithmic curve at an earlier point, maybe. Okay, so one may say that, okay, that is more accurate, because the moment I am talking about using a linear segment, I am invariably talking about some distortion, I mean some kind of change from our desired goal of making the skew-inner independent of the signal statistics. Okay, because in this portion I am using a linear quantizer effectively when the input amplitude is small. So my skew-inner is not going to be really independent of the signal statistics. Okay, so then the approach will be or should be that some linear segment has to be brought in, otherwise this inclusion of 0 becomes a problem, inclusion of the origin. Okay. How many is an issue to be decided. If you think of including more than one line segment, then you are trying to ensure that the SQNR is less dependent on the signal statistics over a larger range of the input signal. Okay. But simultaneously the design may come out to be, practical design may come out to be more difficult, is it not? Increasing the number of segments, because you have to also think of how you are going to implement this, isn't it? Okay. So, I will now mention about two standards which are adopted, where this kind of approximation of linearization for small amplitude of x is invariably there. Okay.
So, will this linearization about the origin help us in boosting the small voltage signals?
It really, see, now try to interpret. Is his question understood? His question is that when I use this linearization, let me say by one segment, okay, for easier understanding, then is it helping us to boost the small amplitude signal? Do you have any answer?
In comparison to large amplitude signal, this is better. So, it is suppressing the higher amplitude.
Yeah. So, there is a relative advantage, because if I use a linear segment here and then uses logarithmic characteristics there. So, it is not that I am following this slope for the input signal, I am not following this logarithmic portion. So, that way I am not boosting the low amplitude signal, okay. But when the amplitude is high, I am suppressing them.
This probability is quite less compared to that low amplitude signal.
So, he has a good point now. What he says is that the probability that the signal amplitude is higher is less usually than the probability that the signal amplitude is lower. Yes.
For a speech kind of signal, we actually having no particular gain over a linear quantizer, because so in the range which will speech signal is usually limited, it is actually behaving as a linear quantizer. So
Not necessarily, not necessarily. It all depends on what is your V. If you design your V, choose your V perfectly. In fact, I started with this general XY curve really. I mean, I should get back to a curve where the ultimate endpoints are limited by plus minus V. So, once those values are fixed, okay, now I mean you can decide about that constant factor k, so that you can reduce this range of linear portion. Okay. So, it is not a very frustrating situation really. There is a constant of proportionality by choosing that value and by considering the two values. When I choose a value of plus b and minus b, I do not choose it arbitrarily really. I expect the input signal to be there. In fact, coming back to his very good point of probability really, in fact, some practical value of plus b or minus b you choose, and there is always a probability that the input signal amplitude may still be beyond plus minus v. So, as we said, as you mentioned sometime back really, we cannot take care of all possible amplitude of the input signal. Usually we decide this value of plus minus v such that the probability that the value is beyond this is very small, negligibly small, okay. Which means that my signal amplitude is likely to be within this, okay. Yes, in general an amplitude probability of this much is less compared to the probability that the amplitude is so low. That is fine really, okay. So, our intention would be to again choose that constant of proportionality such that this linear segment range is not very large really, it is quite small, and hence we can say that we are using a linear quantization for a rather small amplitude variation really, okay. And for most of the amplitude range from that point up to plus v or minus v, okay, we are using a logarithmic characteristic, okay. In fact, that is decided by a constant in the standard values. Yes.
slopes of various segments, that time we are ensuring that even amplitude is suppressed to some extent.
You are talking about a one segment approximation, multiple segment approximation. There the starting segment around 0 will have a slope of 1, okay, and subsequently the slope will decrease. That is what is necessary. So, I was talking about that is a possibility, at least theoretically, okay, for approximating towards this logarithmic variation better than a single segment approximation, okay, fine. but I also would like to remind you that the corresponding implementation may turn out to be very difficult, especially if you are thinking of implementing using analog components. Okay, if you are really thinking of using a pre-distortion circuitry and then a linear quantizer, then that complexity, hardware complexity of the pre-distortion circuitry is going to be involved if you are thinking of using multiple segments in these characteristics. Any other question?
Problem of getting this ln curve, but if we use a simple capacitor,
Louder please.
if you have a capacitor, it already has a ln curve associated with it, and it passes through ln capacitor
A
characteristics.
capacitor characteristics,
And that
capacitor
passes
charging or
through,
discharging. Yes,
that passes through zero also.
right.
So a problem of zero is also not there.
I think he has started thinking about the hardware implementation. Okay, okay, it's good. I'm a good suggestion really. Think of that. Okay, but a simple capacitor does not do this job of pre-distortion. Really. Okay,
So its characteristic is somewhat desirable.
some kind of, yeah, because the capacitor is one component which has an exponential charging and discharging capability. Okay, but the circuit is made of not only one capacitor really. It is made of certain other components as well. Okay. Well, this is one standard expression where, I mean, somewhat deliberately, I have introduced this symbol of x max. I guess I did not use this symbol of x max earlier really. This x max is equivalent to our v plus v, you can say. Okay. This is one standard expression which is known as mu law companding. Okay. It is being followed for quite some time in some countries, especially the US, Japan, Canada. Okay. And as per that, the ultimate expression that has been decided is this. You can see that this part is a normalized expression really, C of mod x divided by the maximum amplitude, that is plus v, okay, is ln of 1 plus mu mod x divided by x max, okay, by ln of 1 plus mu. Can you think a little bit? Here you can say that the magnitude of x is between 0 and 1, I mean x divided by x max, normalized value is between 0 and 1. Okay. So, if I plot mod x by x max along x axis, the maximum value is going to be 1.0, and the corresponding output is C of mod x by x max or v, the maximum output. Let me write as normalized output along the y axis.
Normalized output means Cx by x max.
Yes. Please note down this expression, okay, and tell me in the subsequent diagram what value of mu I have considered in this diagram, where I am plotting the normalized output, that is C of mod x by x max versus mod x by x max, which is my normalized input. So, the maximum values may be 1 or both. Okay. And now I have drawn a dotted line. What is this characteristics? I mean, can you just tell me whether it this is a quantizer characteristics expressed in a somewhat different form in a normalized manner. Okay. And what type of quantizer I am talking about for this curve?
Uniform.
Yes, it is a uniform quantizer, is it not? Okay. Can you tell me the value of mu for this curve? Look at that earlier expression for, yes, that is right. So, for mu equal to 0, we get this curve. Now, try to sketch a value, I mean a curve for some larger value of mu. Yes, please. Tending to 0, yes. Okay. So, when mu is very small really, we get this curve. Okay. But let me tell you, when we use this expression, we hardly go for mu equal to 0 really. Okay. So, yes, at exactly mu equal to 0, there is a problem really, but it tends to that curve really, linear quantizer curve. For practical purposes, we would like to have a value of mu which is much larger. Okay. Can you sketch say for a mu of 100? Yes. Look at that expression.
Sir, for that we have the constant on the right hand side. We have a constant value. We can
Pardon? You get 1 here, no? Is that okay? So, now try to sketch a curve for mu equal to 100 say. Can you sketch and tell me, just think a little bit, whether the curve is going to be, the curve has to pass through these 2 points, okay, whether the curve is going to be like this, like this, lower slope for, I mean smaller slope first and then larger slope later, then there may be some problem really. Then we have to look at that expression back. Yeah, is it not? In fact, with larger values of mu, the curve will be something like this. Okay, if I increase the value of mu further, I can make the characteristic curve look like this even. For higher values, even steeper for smaller amplitude. Okay, and this is the trend for mu increasing. When mu increases, okay, you get steeper and steeper curve for smaller value of x. Okay, let me note here that, no, try a little bit, because then fundamentally there is a mistake really, because if it is low, then I find that small amplitudes are not being boosted up, higher amplitudes are being boosted up really.
So, but mod x by x max is less than 1.
Is always less than 1.
Okay.
So, when mod x by x max is close to 1, the input signal amplitude is large.
So 1 plus mu times that is less than 1 plus mu.
Now, if you think about that, get to that expression a bit slowly. My point is that when this x by x max is larger, closer to 1 really, okay, I mean I am talking about a larger amplitude signal, okay, and a larger amplitude signal, okay, should not give the corresponding gain. If I say the slope really should be smaller and smaller, that is what I am getting here. For the other kind really, when you can just verify from that expression a bit slowly really, there I am talking about boosting the high amplitude signal compared to the low amplitude signal really. So, this is the trend, okay. With larger value of mu, you get a steeper and steeper curve. For smaller value of x, okay, a typical value which is used for design of systems really is 255 for mu. It is one typical value, okay, for a practical system following this mu law companding standard. Okay, and this value incidentally you can see this value, how much, what is this value 255? Did you come across with this value? 2 to the power 8 minus 1, isn't it? Okay. In fact, this value has also been chosen to ensure that if you want to implement your quantizer digitally using digital circuitry, this value becomes convenient really. Okay. There was another value of q, I mean mu, which was also used sometimes, a value of 100, but of late this value of 255 is finding more favor. Yes, please.
is it so that in Canada and US as well they use some packet of 750?
Not necessarily, not necessarily. Okay, that is dependent on how many bits you are giving per sample. Okay, it's more related to that. This value of 255 is closer. I mean, is more convenient, so to say, for the corresponding implementation. Okay, as I said, I mean the value of 100 was also used sometimes. Okay, so this is one standard. the other standard which is extensively used in many other countries and which is a standard from ITU. ITU stands for Telecommunication Union. Okay. So, IT, which is the standard from ITU, which is followed in the European countries and in our country as well, okay, is this expression. In two segments you can see, where again C of mod x in a normalized form divided by x max is shown as a times mod x by x max divided by 1 plus log of a natural log, when this ratio mod x by x max is between 0 and 1 upon a is a constant of course. Okay. That means, when the input signal amplitude is small, then use this expression. Okay. What is this expression? This expression is a linear straight line approximation, isn't it? Okay. The slope is not 1. Okay. The slope is dictated by the value of a. Fine. So, use a straight line segmentation or approximation for smaller amplitude of the input signal, and for larger amplitude this is the full expression. So, when a is beyond mod x by x max, I mean sorry, mod x by x max, when it is between 1 upon a and 1.0, use this expression, which is the logarithmic expression. Okay. Can you sketch that normalized input output characteristics once again for me? Should the nature be different or similar? Quickly. Again the curves will be like this. Okay. Mod x by x max 1.0 1.0 normalized output Cx by x max. Okay. And the curves are like this with increasing value of a, the curve shifts to that side, and here a standard value for this is 87.5, one practical value that is usually followed. A is 87.5. Okay. The nature of the curve is similar to the A law companding, but there are minor there are differences, subtle differences, because this is actually a two segment curve, as you can see. Okay. And get this expression. Okay. Verify yourself that when this is equal to 1 upon a, both the curves they meet very smoothly really. Okay. So, there is no apparent discontinuity over there. So, this is a two segment representation where there is a straight line approximation for smaller amplitude, and then it meets or changes over very nicely to the logarithmic one. Okay. So, these are the two standards which are used, and this kind, when you use this kind of companding operation, we I mean sometimes refer to this kind of system, PCM system with non-uniform quantization as log PCM system, log PCM coding or system. That means, when you use a logarithmic companding algorithm or companding scheme for making the signal to quantization noise ratio almost independent of the signal statistics, we say that we are talking about a log PCM kind of system rather than a linear PCM kind of system.
Mu law was also a log PCM.
Yes, both are log. Mu law companding as well as A law companding, both are log PCM systems. Okay. I will request you to look back these standard expressions and sketch the curves like I try to do here shortly really for yourself, and get convinced that yes, the curves are like that. Okay. Yes. A law companding, this standard which is followed in Europe and many other countries including us, okay, and is approved by ITU, is known as A law companding, because we are using A as the constant here. In the earlier scheme we are using mu, here we are using A. Okay. Do you have any question at this moment? Okay. Thank you very much.